Hello and welcome back. In this video we're going through an example of graphing this curve. It's defined by cosine t I plus sine t j plus 0.4 sine 2t k. So again, we could think of this, excuse me, we could think of this in its component form as cosine t, sine t, and then 0.4 sine 2t, and we're just going to graph this for t between 0 and 2 pi. So one big thing to note already, again, we could just start graphing these. We could just start putting in t values and outputting vectors and drawing these things and kind of getting a picture of it. That's not a terrible way to do it, but a better, more efficient way to do it is to try and recognize some of these two-dimensional curves or three-dimensional surfaces that might be sort of hidden in this vector equation. So that is, what are relationships between the x, y, and z variable? If we can find one or two relationships that hold and we can recognize the surfaces that they tell us, then we'll be able to figure out information about this curve. So for instance, the x component and the y component, that's cosine t sine t, that's very familiar to us. If we square the x component and square the y component and add them together, we get cosine squared plus sine squared, we get 1. And so this represents, if we're thinking of the shadow of this vector valued function onto the xy plane, we get a circle. But remember here, there's no z component. We don't care what the z coordinate is for this. And so what this gives us is a cylinder, a circular cylinder. Right? This is a circular cylinder. It is centered at the origin and has radius 1. So we're on this cylinder. That means this curve is restricted to this cylinder. So curve is on this cylinder. Now, are there any other relationships we can pick out here? Now, this is a tougher one to find. That's why I'm doing this example video. If I take the x component and y component and multiply these together, if you're really good with your trigonometric identities, you might recognize this one. Let me just see what happens if I multiply x and y. So x times y gives me cosine t plus sine, or times sine of t. And that has a relationship to sine of 2t. Remember, cosine t times sine t is 1/2 sine of 2t. That's just another trigonometric identity. And sine 2t is here in the z component. Specifically, the z component, so z is 0.4 sine 2t. So that is z over 0.4 is sine of 2t. And I see that here. So I'm going to go ahead and bring these things together. I have z over 0.4 times 1/2. So this is going to give me z over 0.8. And I'll go ahead and make this look a little bit nicer. 0.8 xy is equal to z. So this is another relationship that holds between the three variables. That is, 80% of the product of the x and y components gives me the z component, always, at all points on this curve. So this gives us a surface in 3 dimensions, right? We have a relationship between our 3 dimensions. This is some surface in 3D. So on one hand, it's on this surface, the circular cylinder. On the other hand, it's also on this surface. So what that means is my curve is going to rely on the intersection of these two surfaces. So curve is also on, I'll say also on this. So conclusion here is that our curve is on this elliptic cylinder, or circular cylinder, x squared plus y squared equal 1, and, or actually I don't want to say and here, is on the intersection of this surface, x squared plus y squared equals 1, that circular cylinder, and this surface, 0.8 xy equal z. Now the 0.8xy equals z, I don't actually expect you to recognize, although it has the form of a quadric surface. So it's got to be one of those quadric surfaces we looked at, but its form is a little bit messed up because this is a rotated version of a surface that we looked at back in section 13.6. One way I can start to recognize this is by taking, say, traces parallel to the xy plane. If I set z equal to 1, what do I get out? I get 0.8xy equal to 1. If I say divide both sides by x, I get 0.8y equal 1 over x. Maybe if I divide by 0.8, it'll help a little bit more to see this. I get y equals 1 over 0.8x. And that's a hyperbola. That's one of those square hyperbolas that I talked about that don't follow the general form of the hyperbolas that we were looking at. This is a rotated hyperbola, or a square hyperbola. So that's why this one's hard to recognize. But if you look at, well, let's just graph it and see what it is. We know at least one of the traces is hyperbolic. Let's go ahead and graph those two surfaces. And then that'll tell us what the curve is generating, or what the curve is. So let's go to GeoGebra here. I'm working again in GeoGebra 3D as I've done in the past. Let's see, where's my x and y? Red axis is x, y axis is green. So I'm going to go ahead and plot my circular cylinder. There's my circular cylinder. I just put in x squared plus y squared equals 1, which is the equation we got out. Right, even if you don't recognize it as a circular cylinder, which you should, but you can always just graph this in GeoGebra and see, oh, yeah, that's right, that's a cylinder. And then I also have this other relationship, 0.8xy equals z. And so I just did this as a function, a of xy equals 0.8xy. I really just put in 0.8x times y, and it gave me this. And what does it give us? It's a hyperbolic paraboloid. You should recognize this from section 13.6. Maybe I'll turn off the cylinder so you can recognize it a little bit better. This is a hyperbolic paraboloid. But the hyperbolas are square, which is why we're not being able to recognize the equation exactly as we see in other hyperbolic paraboloids. It's a square version, or a rotated hyperbolic paraboloid. There's more about rotating axes and getting a hold of, like, actually being able to recognize that equation in one of the projects in the textbook that I haven't assigned. It is really cool to work through that, but not strictly necessary, because we can always just graph these things. So let me turn on my cylinder again, and our conclusion was that the curve satisfied both the hyperbolic paraboloid, this surface, and it satisfied this circular cylinder. It satisfied that surface, so it lied on the intersection of those two surfaces. So can you kind of see the intersection of these two surfaces? Right, dips above and below the xy plane. Maybe you can kind of see the intersection of those two. To help, I'm going to plot our curve. And there you have it. Our curve is right there on the intersection of these two surfaces. So I'll go ahead and turn off both my surfaces, and what we're left with is the curve. That's pretty awesome, right? I mean, you got to admit, that's pretty cool. And we get this sort of, I think of it as like a Pringle shape. I believe the book calls it the roller coaster curve. It's whatever, it's like looking at clouds, right? Whatever you see is what this thing is. So it's very cool. It gives us ways of representing these sort of curves. Now remember, our curve does have an orientation to it, which isn't coming out with GeoGebra, right? GeoGebra is not telling me the orientation of this thing. But if I just go back, remember my x component was cosine t, my y component sine of t. That means I'm traveling in the positive direction, or about the origin, so counterclockwise about the origin. So that means I'm starting here and traveling around. I'll go up a bit, down a bit, up a bit, down a bit, and come back to where I started. The fact that this curve wraps back around to itself means it's just going to keep continuing that pattern no matter what our domain for t is. So t from negative infinity to infinity will also look like this, and so will t from 0 to 2 pi. So on any period of 0 to 2 pi, so even multiple of pi to another, to twice that, we'll always get this sort of curve. All right, that's the idea. That is, I believe, it for this section. I don't think I had anything else I wanted to say. Again, it was hard to recognize the surface in 3D, but we can always just plot them in GeoGebra and then kind of trace our way back. It is a hyperbolic paraboloid. All right. See you in the next video.